I'm looking at 39 where we're titrating a strong acid, 20 mils of a sample, 0.2 molar HBr, and we're titrating that against a strong base, sodium hydroxide. Very important to note, we are titrating strong versus strong. These are pretty straightforward calculations. All the pH is determined by the excess reagent. What are those ions, either acidic or basic ions, in the new combined volume after the equivalence point? Let's take a look at our first one. I'm going to draw out the equation and just kind of tally what we have. We have HBr being titrated against sodium hydroxide. Strong versus strong, of course, there is no hydrolysis. We produce at exactly the equivalence point, the pH would be exactly 7. So let's see where we are after 15 mils of the base has been added. So here's what we're told. We have 20 mils of a 0.2 molar HBr. We're titrating that at this particular moment in time with 15 mils of a 0.2 molar. Let's see what's the limiting and what's the excess reagent. I like to use millimoles, milliliters times molarity. 20 milliliters times 0.2 molar gives me 4 millimoles of the acid. 15 mils times 0.2 molar gives me 3 millimoles of the base. So if I consider what is the limiting and what's the excess reagent, clearly we'd see the sodium hydroxide completely consumed. And along the way, of the 4, 3 were used. We have 1 millimole of acid left. Oops, I should fix that. 1 millimole of the acid ion that's left in solution. Now remember, pH is determined by the negative log of the concentration of the acid ion. Since the acid is indeed the excess reagent, we need to find its molarity. 1 millimole of the acid is left in excess amounts. It's influencing the pH right now, so the solution is still acidic. What's the new combined volume that that proton is found in? Well, 20 plus 15 indeed is 35 mils, the new combined volume. So let's find 1 divided by 35 gives me the molarity of our solution, 0.08257. And if I simply negative log that concentration of the acid ion, the pH, we can clearly see, still quite acidic, 1.54. I'm carrying 2 decimal places so far. Strong versus strong, the excess reagent determines the pH. Let's suppose we're at 19.9 mils. I'm going to just put on a piece of paper so I can write larger. So I'm going to just cover that up. 19.9 mils, and again, I like to just tally what we have going on. We have HBr, NaOH. Doesn't even really matter on the product side because strong versus strong, the products will never influence, where that's not true if we have weak versus weak or so forth. Now I still have titrating 20 mils of a 0.2 molar HBr, which still is 4 millimoles of our acid. But now I've gone from the 15, I'm having 19.9 mils of the base, its concentration still 0.2 molar. How many millimoles of base have we yet to add? Well, 19.9 times 0.2 gives me 3.98 millimoles. It is still the limiting reagent. At that point, the sodium hydroxide is consumed, but we still have an excess amount. It's tiny, but we still have an excess amount of the acid. How many millimoles remain? Is 0.02 millimoles. So again, the acid is an excess amount, so pH can be calculated directly by taking the negative log of the concentration in millimoles over new combined volume. We had 0.02 millimoles of the acid ion, excess amounts, and the new combined volume is 20 plus 19.9, giving us a total of 39.9 milliliters. So if we consider 0.02, let's just hit that together. 0.02 divided by 39.9 Negative log that answer, and we have a pH of 3.299, so 3.30. So upon the addition of a few more mils, we're getting more basic. We're adding more base, 1.54. Now all of a sudden we're at 3.30. Alrighty. In the next part, we have exactly 20 mils. So if I consider what's going on here, again, I like to tally what we have. So HBr was sodium hydroxide, strong versus strong. We know we still have 20 mils of our acid at 0.2 molar. That's 4 millimoles. But the base now is also 20 mils. It's also 0.2 molar. It is exactly 4 millimoles. Clearly we see in letter C there is no limiting or excess reagent. They are both going to be consumed equally. So what is the pH? Keep in mind there is no hydrolysis for strong versus strong. We have both parents that are strong, so there's nothing influencing the pH. Strong versus strong at the equivalence point is exactly neutral. pH is 7. It is not acidic nor basic. Then what happens? We exceed the equivalence point. We've added more base. So at this point in the journey, we'll come down here. Let me slide this up. We still, I'd like to do this. I like to keep tally of what is going on. HBr, we know we have 20 mils of a 0.2 molar. That is still 4 millimoles. And now we've added 20.1 mils of base, its value 0.2 molar. So find out how many millimoles. We've gone past the equivalence point. So now we're looking at, I didn't hit that right, 20.1 times 0.2 molar is 4.02 millimoles. So clearly we see that the limiting reagent has now switched to the HBr. It's completely used, and along the way it's consumed 4 of the 4.02, so we have 0.02 moles of base ion left in solution. The molarity can be found by taking that excess reagent, millimoles, which is the base, over the new combined volume, 40.1 milliliters, millimole over milliliter. So our 0.02 divided by 40.1 gives us the concentration. 0.02 over 40.1 gives us the new concentration. I'll just write that down, 4.99 times 10 to the negative fourth. Remember, that's the base, isn't it? So when I negative log, I'm getting something called the POH. Negative log that answer, and we find POH is 3.3, so my pH is 10.70. When the base is the excess reagent, you see a big jump very quickly past the equivalence point up into the basic range. We've overshot the endpoint by 0.1 milliliters. Look at the swing in the pH. It's quite significant. And well past the equivalence point with 31 mils, here we could take our HBr and sodium hydroxide. We had a 20 mil sample, 0.2 molar. Here we have a 31 mil sample, 0.2 molar. Let's find how many millimoles. Of course, the acid has been consistent all along, 4 millimoles. 31 times 0.2 gives us 6.2 millimoles of base. Clearly you see the acid is consumed, leaving us a remainder of 2.2 millimoles of the base ion. 2.2 millimoles of our base over the new combined volume of 51 milliliters. 2.2 divided by 51 gives us the concentration of the base ion. And therefore, to find pH, we'll negative log, and remember to take 14 minus. So when I'm considering giving excess base ions, just remember the 14 minus trick at the end. So negative log that answer, and that's our POH. 14 minus that is our pH. pH now is well up into the base range, 12.63 pH units. Pretty straightforward calculations for strong versus strong. Nothing to consider in terms of conjugate pairs and hydrolysis and so forth. That's not the case when we go on to the next question. Here's example number 41. So 17.41. Now I'm titrating a weak acid with a strong base. Weak acid, strong base. The salt of a strong parent base will not hydrolyze, but a salt of a weak acid certainly will. So let's take a look. I'm going to work again on a separate sheet of paper just to give myself a little more room. We have a pretty straightforward Ka problem, looks like here. So let's see. We have acetic acid being titrated with sodium hydroxide. Alrighty. What we have is 35 mils of an acid with 0.15 molar concentration. We have 0 mils of the base being added. It's also at a value of 0.15 molar units. So clearly, since no base has been added, all we're looking at here is what is the initial pH of the acetic acid. pH can be found by a simple Ka problem. We need an appendix D to look up some Ka values. Ka for acetic acid is 1.8 times 10 to the negative fifth. So I needed that chart to know that. Appendix D is giving me a Ka. Since no base is added, this is the only thing influencing the pH. So truly what we're looking at is an old-fashioned equilibrium problem where an acid partially ionizes to create conjugate pairs. I know this value is 0.115 or 0.15 molar. So from our previous chapter, straight Ka problem. Let's call the hydrogen ion X, the acetate ion X. Technically this would be 0.15 minus X, but we can check that 5% rule. So the Ka, 1.8 times 10 to the negative fifth, is equal to X squared over 0.15. X is denoting the hydrogen ion. 0.15 times 1.8 e negative 5, square root that answer, and the hydrogen ion 0.00164. Let's just quickly check that 5% rule. It's 1% ionized, so we fall well within the 5% range. Now, since I know the hydrogen ion, we simply negative log the 0.00164, and we have our pH of our weak acid, 2.79 pH units. So no base added, straight Ka problem, old-fashioned from chapter 16, the acid-base unit. Now all of a sudden we open the burette and we allow base to partially neutralize the acid. Let's see what now is going on in terms of what's the limiting and what's the excess reactant. I like to tally what we have. I encourage you to do the same thing. Now you know that sodium would be a spectator, so we could truly eliminate it and write our equation in terms of a net ionic equation as well. Here we still are having 35 mils provided of the acetic acid, 0.15 molar in strength. Over here we have 17.5 milliliters of the strong base. That's also 0.15 molar in strength. How many millimoles are present? I have 35 times 0.15. There are 5.25 millimoles of our acid. I have 17.5 times 0.15, 2.625 millimoles of base. This is our initial millimoles of each of our ingredients. We can clearly see that the base is the limiting reagent. It's going to be used until it's completely gone, giving me 0 hydroxide ions. We also know that this reactant would decrease at 2.625 millimoles. How many would remain? Exactly half, 2.625 millimoles of the acid. We know that water would drop out. What about this acetate ion? The acetate ion is a product. We know that products get made. It's going to be made at a tune of 2.625 millimoles. So at the end of this delivery of base during our titration, we've also produced 2.625 millimoles of the conjugate base of our acid. Both of these influence the pH. This looks like the job for the Henderson-Hasselbalch. pH is equal to the pKa plus the log of the ratio of base over acid. We'd like to know the pH. We have a conjugate base and we have a conjugate acid, both in solution. And if I consider what's going on, P is negative log. Remember, our 1.8 times 10 to the negative fifth is the Ka of acetic acid. But I notice that at this particular volume, the number of millimoles of the conjugate base and the conjugate acid are exactly the same. When that happens, that simply drops out, doesn't it? At this particular moment in time, when we delivered exactly 17.5 mils, I'm at equal millimoles of acid and conjugate base. Negative log of the Ka, negative log of the Ka delivers for me the pH, 4.74 pH units. What if we added 34.5 milliliters to this solution? Let's see what we have now. Again, I like to keep track. We need to keep track of what millimoles are present. And again, I can choose to leave off the spectator, knowing that a water molecule forms and we're left with a conjugate base, the acetate. Alrighty, so now we still are using 35 mils of a 0.15 molar hydrogen acetate acetic acid. Now I've added 34.5, almost to the equivalence point, aren't we? Milliliters, and this is also 0.15 molar. How many millimoles are present? So we'll just re-hit again. 35 mils times 0.15. That was our 5.25 millimoles. Did I do that right the last time? 5.25, that's right. I thought, man, that sounded new. Let's keep going, almost to the equivalence point. Here we have 34.5 mils of base times 0.15. So we have 5.175 millimoles of the sodium hydroxide. So clearly we see this is still going to be used first. The limiting reagent runs out first. There's no millimoles left of the strong base. Of the 5.25, 5.175 millimoles of the acid were consumed. How many remain? The difference between 5.25 and 5.175. That's 0.075 millimoles of the acid. How many millimoles of the conjugate base were produced is 5.175. Remember, this determines everything, the limiting reagent. So at equilibrium here, we have 5.175 millimoles of the conjugate base. Both of these influence the pH. When I have an acid and its conjugate base in solution, it's the job for the Henderson-Hasselbalch. pH is equal to pKa plus the log of the ratio of the molar concentration of base over acid. We know that negative log of 1.8 times 10 to the negative fifth is how we'll find for pKa, negative log of the Ka value for acetic acid, plus the log of the ratio of base over acid. Notice, friends, that I am leaving it in a millimole ratio, which mathematically is fine. Remember, if I were to put these over the new combined volume, I'm dividing both by the exact same number, and algebraically they would simply cancel each other. So that ratio would be the same, regardless if I put it into molarity, because they are exactly in the same number of combined volume mils. So it is okay to leave them in millimoles. We're going to get the same ratio. It is not okay to leave them in a millimole when I'm solving for pH directly, but if it's in a ratio, the math allows us to do that. Alrighty, so let's begin solving for this. Here we have the ratio 5.175, the conjugate base, divided by 0.075, the conjugate acid. The ratio, I'll just take the log of that answer and add that to the negative log of our Ka value, and we'll find the pH. And I'm finding 6.58 pH units, still in the acid range. We've not yet reached the equivalence point. What about exactly at the equivalence point? Letter D. Acetic acid plus a strong base produces, let's get rid of that spectator, produces a water and the acetate ion. Both of these influence, don't they? Now all of a sudden I'm noticing I have equal volumes of an equal molar solution. We're exactly at the equivalence point. 35 mils of a 0.15 molar, and we have 35 mils of a 0.15 molar. We have the same number of millimoles. I don't remember, so I'll hit again. 5.25. And that's the same for both, isn't it? But it's not, let me repeat 1,000 times, it's not going to have a pH of 7 as a strong versus strong does, because we have the influence of this conjugate base. So I know that the only thing left in solution, this is gone, this is gone, but we made 5.25 moles, millimoles, of the acetate. So in solution, we have something in there that is influencing the pH, and that's a hydrolysis problem. This here is the chemistry. This is what we now target to find what exactly the pH of our solution is. So when acetate undergoes hydrolysis, We know that the proton combines back on to create its conjugate acid, but that the solution then is left a little bit basic. The hydrolysis portion from our previous chapter. That means that this is Kb chemistry, isn't it? It's a basic solution. So I have to flip my known Ka into a Kb. So I know that the Ka multiplied by Kb is always this constant where we have Kw. So I just want to flip my Ka from our previous problem, 1.8 times 10 to the negative fifth, into the Kb. So let me do that for us. 1e negative 14. I'm going to divide out our known Ka, 1.8e negative 5. Negative 5. And there is the Kb for our value. Kb is 5.56 times 10 to the negative 10th. This is Kb chemistry, isn't it? So now what do we know? I have 5.25 millimoles of this acetate ion in a new combined volume of 70 milliliters. Alrighty, that new combined volume is critical here because I don't have a ratio of base over acid as in the Henderson-Hasselbalch. I need to know its actual molar concentration. So 5.25 over the new combined volume of 70 gives me a molarity of 0.075. Let's call this X, let's call this X, and set up a Kb expression. 5.56 times 10 to the negative 10th is equal to X squared over the new volume, the new molarity we found by millimoles over combined volume. Alrighty, I'm going to cross multiply square root. Remember what we let X stand for? It's the base ion, OH negative. 5.56 E negative 10 times 0.075. Square root that answer, and I'm finding the hydroxide value to be 6.46 times 10 to the negative 6th molar units. Now let's work to pH. Negative log that, and I get POH 14 minus, and I have my pH. Makes sense. The base ion was dominating. It should land in a base on the pH scale, 8.81 pH units. So here's what we've just kind of worked through, a process where exactly at the equivalence point it turns into a hydrolysis problem where it's the only thing left in solution is the conjugate base from the original acid. It turns into a Kb problem. Previous we worked Henderson-Hasselbalch. At the equivalence point it's hydrolysis. Now look what happens. When I overshoot the endpoint, let's take a peek now. I've got 0.5 mils. I'll just write it right on here. I have C2H3O2 with OH negative giving me water and the acetate. Alrighty, but now all of a sudden we've overshot the endpoint. Let's take a peek how I know that. We have 35 mils of a 0.15 molar acid. Now all of a sudden we have 35.5 mils of a 0.15 molar strong base. Alrighty. Clearly I'm seeing that the base has now become the excess reagent. So let's see, how many millimoles of each do we have? I have 5.25 millimoles of our acid. 35.5 times 0.15 is 5.325 millimoles of the base. The acid is gone. It is now the limiting reagent. Along the way, it's used minus 5.25. It's used up 5.25 of the 5.325. I have 0.75 millimoles remaining. And now all of a sudden I go, oh, excess reagent is the base. And the base was strong, Don't care about anything else. The strong will dominate the influence of a pH. I just now will say, okay, what's the pOH? It's simply taking the negative log of the molarity. It's not Henderson-Hasselbalch, so I need a new combined volume. 35.5 plus the original 35, we have 70.5 mils. Let's find the pH. 0.75 divided by the new combined volume gets me the molarity of the base. Negative log that gets us pOH. Flip it to pH. Quite basic. pH is 11.026 pH units. 0.03 would have been better. Great. You have one more on this section. We have 50 mils of the base. Very similar to letter E. Let's work this one together. We have acetic acid with a strong base, giving us the conjugate base, and water. We know that we all through consistently 35 mils, 0.15 molar, giving me 5.25 millimoles. How about for the base? Here we've added 50 mLs. I'm working this one. 50 mLs. Just ran out of room, so I'm putting new paper up. 0.15 molar. How many millimoles are there? 7.5 millimoles. So again, the acid is used. It is the limiting reagent. 7.5 minus the 5.25. Tell me how many millimoles remain of that strong base, which is 2.25 millimoles. Since this is strong, I don't care about any kind of Ka, Kb's, the strong, straightforward chemistry. I can find pH by simply taking out the new molarity of that excess reagent, 2.25 millimoles, the new combined volume, 85 mils. Of course, we know this is base, so when we hit for this, we know it's pOH. We'll easily flip it to pH. So that new molar concentration, 0.02647, negative log that answer, and we get pOH, 14 minus that answer, and we have pH, 12.42 for that final pH. Now my work was a little bit messy. Hopefully I gave you enough room to kind of work through. Feel free to add and attach additional sheets. I'm going to pause the lesson here, give you time to process. We've worked through 2 titration problems, strong versus strong, and the second one, weak versus strong, weak acid, strong base.